Hello, so in this video we're going to talk about derivatives of logarithmic functions. Now, a logarithmic function is what we say the inverse of the exponential function, which means that in a way it's like you have that you're going from one form to the other. So for example, if I have log base of ax and that's equal to y, well, I can actually change it from what I call logarithmic form to exponential form by kind of like doing the following, where we just rewrite it as a to the y equals to x. So essentially, I have that this is our log form, and this is our exponential form. Interestingly enough, you can do the same thing with numbers, like 3 to the 4th equals 81. It's just notation. So we look at log base a of x, where the domain is strictly positive from 0 to infinity, and we have that the base must be not only not equal to 1, but it has to be strictly positive. So this is what the equation of the logarithmic function looks like in the x and y plane. But really the question becomes, for instance, like how do we find the rate of change for the derivative of the logarithmic function? You can tell that this function is actually increasing on its entire domain, but because it's the kind of like the opposite of the exponential form, like for instance, if I was to graph the exponential form, you would see that the exponential form looks something like this. So if this one is moving at a faster rate, then that means that this one is moving at a slower rate. So this actually increases at a much slower rate as opposed to the exponential function. So that's just a little detail that, yeah, you can kind of take with you about derivatives of logarithmic functions. Now, the way that I'm going to go ahead and propose the problem, so like, we have that we want to find what's the derivative of log base a of x because, yeah, it'll be useful. But the question is like, okay, how do we find that? So how do we find that goes to that, well, I know that y equals to log base a of x, but I also know that it has a logarithmic or exponential form. So in this case, we'll just go ahead and rewrite this so that we can get y, not y, but a to the y is equal to x. So we're going to differentiate this. So we differentiate this with respect to x, as mentioned. And what we get is the following. We get that this is going to be the derivative of a to the y, which in this case, that's just going to be a to the y, but multiplied by dy dx. Okay, now the other thing of which that we would have is that this would be equal to 1. Now, I actually did forget one little thing right here. We're going to need to put ln of a multiplied by a to the y because in the previous chapter, which I didn't show in the previous video, is that the derivative of any function like a to the x, it's equal to ln of a multiplied by a to the x. So in this case, this would be ln of a times a to the y. So we'll go ahead and rewrite this as dy dx is equal to 1 divided by ln of a multiplied by 1 over a to the y. But a to the y is equal to x. So that's going to be 1 divided by the natural log of a multiplied by x. So we actually have our formula as it relates to derivatives of logarithmic functions. So basically we have that the answer to the question is that the derivative of any logarithmic function base a of x is equal to 1 divided by the natural log of a multiplied by x. Now, of course, that would be the same for chain rule. Okay, so that gives us the derivative of that function. Now, one thing that you'll note is that ln of e, or let's say like ln of x, ln of x is the same thing as log base e of x. Now, one thing though is that if we have, for instance, like ln of e, that's actually equal to 1. So what that does is it also tells me that if I'm taking the derivative of natural log of x, it's going to be equal to 1 divided by natural log of e times x, but that's really just 1 over x. So that tells me that the derivative of the natural log of x is just 1 over x. Now this is only valid for, say for example, when x is positive or negative for that matter, but we're actually going to get into that for instance. Now I'd like to at least do a few examples. So we'll go ahead and look at how we can find the derivative of log base 3 of x. So log base 3 of x, if we go ahead and we just say, well, for example, that's really just where a is equal to 3. So I automatically know that this is going to be 1 divided by the natural log of 3 multiplied by x. So we can probably just rewrite this as 1 over ln of 3 times 1 over x. And then that would be it. Now, because I didn't really show, for example, like what was the derivative of the power function, I'd like to, just take a step back and just go ahead and look at it again. So for instance, let's say that you did have a to the y equals to x. You can actually just say that ln of a to the y equals to ln of x, and then now you have that this will be y multiplied by the natural log of a equals to the natural log of x. When you differentiate on both sides with respect to x, you actually get that this is going to give you dy dx, and then you have the ln of a is still there because it's a constant. So that gives you 1 over the natural log of a multiplied by the x, because the derivative of ln of x is just 1 over x, so it pretty much gives you like the same thing in terms of like the derivative of the log function. And for that matter, it allows you to basically know what the derivative of a power function is as well, in addition. So in case like you didn't see it written down for the first or for the previous chapter, you now know like how exactly do you take a derivative of an exponential function when it's a base a. Okay, so let's say that we want to try another example where we have find y prime for y equals ln of negative x. Now this one's actually pretty interesting because it's wanting you to basically find the derivative of the reflection of ln of x, But, that really shouldn't matter in terms of like what it's going to be, because essentially you have that the graph looks the same. The only difference is that it's reflected. So in that sense, the question becomes like, will it be the same? So when we take the derivative of our function, we're just taking the derivative of natural log of negative x the exact same way. So that would be 1 divided by negative x multiplied by the derivative of negative x. That's just chain rule. So that gives me negative 1 over x multiplied by negative 1, but that's the same thing as 1 over x. So the derivative of minus, or natural log of minus x, it's still just 1 over x. So in that case, that leads me to the following. It leads me to that, really these are rules. So we have that this gives us that the derivative of, let's just kind of summarize so far, log ax is equal to 1 over ln of ax. But for that matter, we should know that the derivative, if it was like a chain rule, like log base a of u, it's going to be 1 divided by ln of a multiplied by u, but then you got to multiply by du dx because of chain rule. Then I know that, I also know that the derivative of, okay, so this is where it gets a little interesting. So we'll just say ln of x, absolute value, because that's going to account for the positive and the negative. It's 1 over x, followed by, followed by, we have the derivative of ln of u. If you have the derivative of ln of u, that's just 1 over u multiplied by the derivative of u, but with respect to x. So this is actually going to be pretty useful as it relates to your different formulas, or just derivatives for that matter. So we'll just try this example where we have find the derivative of natural log of the absolute value of 2x, and then we just want to find that. Okay, so accordingly, this is going to be equal to 1 divided by 2x multiplied by the derivative of 2x, which is just really 2. So it's going to give me 1 over 2x multiplied by 2 over 1, but that's the same thing as 1 over x. So, I mean, this is just an example that we just demonstrate that no matter what it is, it's always going to be the same thing. Now, there is a nice property that you could have used, for instance, to find this derivative. You could have rewrote natural log of the absolute value of 2x as natural log of the absolute value of 2 plus natural log of the absolute value of x. When you take the derivative of this, you would have saw that that would have been a 0, and that would have just been 1 over x, which is more or less the exact same thing, because the derivative of a constant is just 0, and then you're just using the derivative of natural log of x, so it's just 1 over x. So that actually seems a lot faster in a sense, because we're not assuming using kind of like the quotient rule, or anything like that, or maybe even reciprocal rule, I don't know. No, it's not exactly a reciprocal rule. Okay, so let's say that we go ahead and we try to find the derivative for f of x equals to log base 3. Actually, let's just change this up a little. Okay, so we'll actually, we can probably just say that this is going to be log of, okay, so we have the absolute value of x squared plus 5x plus 4, all divided by x squared minus 5x plus 4. And then we have the absolute value. Now, notice that, for instance, that in finding the derivative of this, it's going to require a little bit of chain rule and quotient rule, and that might be too much. So what we could do is just say, well, log of the absolute value of x squared plus 5x plus 4 divided by x squared minus 5x plus 4 is the same thing as log of, okay, well, let's go ahead and just factor this whole thing. So the top part factors as x plus 1 multiplied by x minus, no, minus plus 4, all divided by x minus 1 and x, yeah, minus 4. Now, furthermore, this actually becomes log of the absolute value of x plus 1 and then x plus 4 minus log of the absolute value of x minus 1 and x minus 4. That should be absolute. Now, this furthermore breaks down into the sums of the products. Okay, so, or products go to sums. So we have log of the absolute value of x plus 1 plus log of x plus 4. Okay, so that should be an absolute minus log of the absolute value of x minus 1 minus, because these two are added, so it's going to be minus also. So that's going to be log of the absolute value of x minus 4. But now, when we take the derivative of all of this, so let's just say that this is equal to y. So y prime is going to be as follows. It's going to be 1 over x plus 1. Why? Because by definition, it's always 1 over what's inside times the derivative, which is just 1, minus 1 over x plus 4, but times the derivative of x plus 4, which is just 1, minus, no, that should be a plus, minus 1 over x minus 1 times 1 minus 1 over x minus 4 times 1. Now, this is all the derivative in that case, but there is one thing that we're missing. We're missing that this whole thing has to be multiplied by 1 over the natural log of 10. So in any case, like if we kind of clean it up, we end up with 1 over natural log of 10 multiplied by 1 over x plus 1 plus 1 over x plus 4 minus 1 over x minus 1 minus 1 over x minus 4 minus 4, which that's the whole answer. Now it might look a little messy, but in some cases it works for most, that you can just say it's just 1 over 1 over 1 over 1 over 1 over. But you know, it's just preference really. So if you want to, for instance, like kind of just remember back to like what were the properties, I would say, like, you know, just review the properties of logs. Like for instance, like you have log a x to the n, that equals to n times log ax. If you have like log a, that's equal to 1. If you have log a, um, let's see, yeah, log a1, that's equal to 0. And then if you have, let's say, log base a of x times y, this is the one that goes to addition. And then furthermore, if you have like log base a of x over y, This is the one that goes to subtraction. So if anything, reviewing some of these properties of logs will help you. And then, just remember the whole formula for exponential form and logarithmic form and how you can differentiate um, in in any case, like whether it's base A or base E.